Hi everyone, I'm Kartik and today I'm going to present the AlphaStar paper by DeepMind. So, like AlphaGo, this also caught media's attention because the group is now trying to solve a more complex real-time strategy game called StarCraft. Vinyls and his team published this in Nature last year and I am happy to present it. Okay, so just to give you an outline of the presentation, we are first going to go over StarCraft II, the game, give you an overview, and talk about an interface which was developed for machine learning application. Next, we're going to give you an overview of the AlphaStar model, talk about the supervised learning components of it, the reinforcement learning components of it, and the agent architecture. Next, we are going to describe the results in detail and have some final remarks. So, StarCraft II, what makes this a complicated game? In a nutshell, it's three reasons. The first one is imperfect information, meaning even though you may have a good idea of what your units or agents are up to, you don't always have the complete picture of what your opponent is doing. Next, agent coordination, meaning you have to control multiple agents to perhaps achieve a common task. So, this may be difficult because each of those units or workers have their own capabilities. Next, long-term reasoning. So a typical game like this lasts around 10 minutes. That means that only after thousands of actions, you get to know whether you win, lose, or tied in the game. So you need to be able to make high level like strategic decisions, and this requires long-term reasoning. Okay. So the most common way of playing this is in a one versus one setting where each of the players choose between one of the three races. So the first one is the Protoss. This is intelligent alien species, whereas Terrans are basically humans in armored suits. And finally, we have Zergs, which are these ugly insect-like creatures. Okay, and each one of them again have their own unique abilities. So it's not that one particular race is at a disadvantage compared to other. And this is what a typical gameplay looks like. So as you can see in the bottom left here, the minimap shows the entire map, but only at a high level. But on the screen here, you can see a section of this map in detail and take actions. Okay, so this is a professional player, and as you can see, the number of actions that this guy is making is seems pretty huge, right? So this is an intense game, and a professional player roughly makes like 300 actions per minute or APM. Okay, now let's talk about Pi SC2. So since its release by Blizzard and DeepMind nearly 3 years ago, there have been a lot of developments, and this has provided a good playground for researchers to develop and train agents in StarCraft. So it has several benefits. The first one being it provides a Python interface, so it's really good for working with deep learning libraries like Keras, TensorFlow, PyTorch, etc. And they also provide a huge number of game replays. So these are humans playing against each other, and your agents can perhaps learn a lot from these kind of replays, that the actions they are supposed to make, the units they are supposed to build, etc., etc. Then they have also created mini games or maps which have mini games to basically tackle simpler problems. So if your yeah, if your agent is perhaps not capable enough, or if you do not have enough computation power, you can start by solving this mini games, which are, as I said, easier to solve. Then I guess the main benefit of Pi SC2 is that it provides a certain level of abstraction. So as you can see over here, this does not look similar to the StarCraft II engine, the frames which StarCraft II engine renders. So they have abstracted away the graphical details, the VFX information into these feature layers. So into these feature layers. So each one of those feature layers shows some different units, the area or the regions which have been observed, etc. So as you can see, one example here is the section of the minimap which is being shown on the screen. So there are these different feature layers, which from a computer vision perspective makes this problem way simpler than the original problem, but from an action decision making perspective or a reinforcement learning perspective, this so does not compromise much on the original goal of learning StarCraft 2. Okay, they have also grouped together some actions, so something like selecting a rectangle and moving them to a coordinate. So selecting some units and moving them to a coordinate requires multiple clicks in the actual StarCraft 2 game, let's say, but here they have created a single bundled action for that, so something like that. So they have grouped certain actions as well, and they have a lot of these other abstractions. So yeah, it's pretty useful as a framework. Okay, now we'll talk about StarCraft, and this is what the entire loop or working or the inference stage looks like. So this is your AlphaStar agent, and it makes some action, and there is a monitoring layer which basically decides when to take this action. They are trying to limit the actions they make, as I'll talk about like in a minute. And once the delay is completed, the action is made through the SC2 engine, the interface we just talked about, and based on the new observations, the AlphaStar again makes a decision. Okay, so this 30 millisecond delay, as you can see, is like the forward pass delay for this agent, whereas this 80 millisecond is including all the interactions with the StarCraft engine, the PySC2, and all of that. Okay, so with this project, they had certain goals in mind. The first one was reaching Grandmaster level, because no other automated system or agent has reached perhaps even the master level, and they fare really poorly against human players. So their goal is to reach the Grandmaster level and perhaps beat all humans. Okay, and while doing so, they also want to have human-like constraints, which means they only want to have partial view. So they, at every instance, they do not know what the opponent enemies are doing, right? So this is again a partial view that makes it closer to what humans see on the screen while playing the game. Okay, then they have monitored actions per minute. So as I talked about, this is limiting the number of actions which can make, plus the network itself has some delay built in. So again, all of these are just to make this problem in a setting which is more human like, right? So that you know that the AlphaStar is actually learning good strategies rather than just bombarding StarCraft 2 with actions. This is like the conclusions or the main takeaway from this entire project, and we're going to describe those individual items in detail in the further slides, but this is just to summarize what AlphaStar has provided us. So the first being that it is a large scale study, meaning given powerful infrastructure and a good agent, we want to see how far we can take this reinforcement learning approach to solving this problem. So this serves as a good test bed for doing that. Then they have also realized the importance of prior information, so supervised learning or imitation learning more specifically, which we're going to talk about. Then they have also demonstrated the robustness of reinforcement learning training methods. More specifically, it is a leak training method which they have developed, which is based on self-play techniques. And finally, they have done an analysis of the architectural components to realize which tools or which mechanisms make sense for this kind of agent. Okay, so at its core, this policy network is something which takes in a state and a statistic z uh, to make an action, right? So the state itself contains observation up until this moment at any given instant, and the action is basically all the actions which have been taken right before that step, right? So given the state and a statistic, we determine the action. So I'll talk about statistic in the next slide. And again, this is parameterized by theta, which is a neural network in this case. Okay, so supervised learning. This is what the supervised learning training loop looks like. So you have human data, and we have a lot of that, right? So as we discussed, the main objective here is to try to imitate the nearly 1 million game replays which are available with PySC2, right? So yeah, so what we are trying to do here is we are asking the agent to make actions or even determine the order of actions similar to what humans make. So That's the ultimate objective here. Then statistic Z. So this is pretty important to understand, and it includes the several things. So the main component being the build order of all players. So let's say you have this 1 million or so games, right? So if you have seen that a lot of the players are building some kind of units or bases in the initial stages versus, let's say, a particular kind of unit like a drone or a stalker or something like that. So you want to have that build order in mind. So it makes sense whether you want to build some units in the initial phases of the game versus in the later phases, if that makes sense. And that more specifically includes the first 20 buildings being made, units being created, the upgrades which are made available, etc., etc. So this statistic based on those 1 million games is pretty important, as we'll see. Okay, so the objective is to minimize the KL divergence, and this is between the two distributions of human actions and policy prediction. So as you can see, this policy predicts taking some action, and you want to align that closely with the corresponding human action, right? So this is popularly used to bring two distributions close together. Okay, so after this initial training, they have also fine-tuned it on the top winning replays to just improve the performance. And just as training details, they have used the Atom optimizer and L2 regularization as well. Okay, now we're going to talk about the reinforcement learning and give you an overview. So some details are included in the next slide, but we'll just give a high-level overview of the RL part of this. So this is what the training regime looks like. And the AlphaStar agent here has been initialized from the supervised learning model we obtained from the previous stage, and this RL training improves that model. Okay, so specifically they have used the asynchronous advantage actor critic, or the A3C method, and within that the reward which they get is the only reward which they get from the SC2 engine is just a win or loss or tie at the end of each game, right? So that's a -1, 0, or +1. Okay, so as you may be able to see here, the reward sparsity is a big issue, and they have done a lot of things to alleviate that. We'll see them now. Okay, so before that, backing up, so the actor learns a policy. In the actor critic method, the actor learns a policy, meaning it basically learns to pick good actions, whereas the critic learns to estimate good returns or good value for a given action, right? So it's crucial that you improve both of them, and this actor critic method achieves that. Okay, specifically for updates, for the critic, they have used TD lambda learning, and for the policy, they have used a combination of vtrace and something called upgo introduced in this paper. Just to note here that the critic uses opponent information, as you may be able to see here, but since the critic is actually discarded during inference, it shouldn't be that crucial, because the critic is only taking the opponent information to provide useful feedback to the actor, right? Because at the end of the day, during inference, all we want to do is pick good actions, and we don't really care about the return we are going to get here. Okay, so again, so since reward sparsity is an issue, the first thing they did was have the KL divergence minimization included in this phase as well. So this is initialized from the supervised learning model, and this is frozen at the supervised learning stage. So again, they are trying to keep the policy predictions closely aligned via KL divergence minimization. Okay, and another thing they have did is introduce pseudo rewards. So this is based on the statistic Z. So as you can see, this Z statistic is fed into the network, or rather they have tried to minimize the edit distance between the actions which the agent chooses to make, and and whatever the statistic says. So something like an edit distance, meaning how different or how many actions different is what is suggested versus what is actually predicted. Okay, and each one of those pseudo rewards, they have multiple of those, so each one of those pseudo rewards is active 25% of the time. So again, all of this is just to deal with the problem of reward sparsity and provide more incentive to be close to how humans take actions. Okay, now we'll go over the reinforcement learning details. So at its heart, this is an actor critic model, and these have been usually popular in recent reinforcement learning experiments and projects. So both policy based and value based are important model free RL techniques, right? So the policy based methods try to obtain an optimal policy, so something that takes the best action possible, versus the value based methods, for given any action, they want to best estimate what is the expected value or return possible from this. So actor critic combines both of them. Advantage actor critic is just a simple reformulation wherein instead of q values, they try to predict or estimate the advantage values. This turns out to be a bit more stable. That is why A2C is preferred over AC in many cases. Next, the asynchronous A2C or A3C is simply a hugely parallel experiment of A2C. So yeah, we'll see the details in just a bit. Okay, so this is what the cost function gradient looks like for the actor critic method, and with the A2C reformulation, as you can see, it looks pretty close to the original formulation, but instead of a Q value, you have the advantage values over here. Okay, and this is the A3C. It's pretty interesting. So you see, we have a single global network over here and multiple independent workers. So this worker has the same structure and they have their own independent environment. They interact with the environment, and based on the updates they have made, they they communicate these updates to the global network. And what's interesting here is that they reset to the parameters of the global network. So in this way, each one of those workers are independent, but they are indirectly communicating with each other, and this provides a hugely parallel playground, something which has proven to be very advantageous. Okay, so this again is off policy learning. So there are certain issues with the trajectory this global network is following. So vtrace is one of the methods which actually tries to correct this using some n steps as it is determined. So vtrace is one of those. And in this paper, upgo is introduced, which is a form of self imitation, because in some cases when vtrace take a bad decision, we basically are ending up in taking worse and worse actions. So it just tries to set a cutoff that if the action taken is worse than average, they use a self imitation policy to prevent from that and move in a better direction, as I understand it. Okay, finally, TD lambda learning is used for the critic. These two above were used for the actor. So the TD lambda learning is somewhere between the the full episode exploration, or like the update after full episode, which turns out to be a Monte Carlo, versus a single step. So it is somewhere between that. This is how I understand it. Okay, let's talk about leak training, which is pretty core to AlphaStar and the performance it is able to achieve. So the first concept here is self-play, meaning agent playing against copies of itself so that each one of them can improve over time. Fictitious self-play, or FSP, is where agent plays against past versions of itself. So since self-play has this problem of moving in cycles, fictitious self-play alleviates that. But prioritized FSP is another improvement on that, in that the agent chooses players in the past which it is more likely to be defeated against. So it means basically it is picking harder battles, right? So this is something which the paper proposes, and there are like a couple of ways of doing it, but at its core, it is the agent is picking difficult past versions. Okay, so let's say this is what self-play training looks like. wherein this unit overpowers this, which overpowers this, and this turns on in a cycle. So as training progresses, you can see it is getting biased towards creating uh, units of this particular type, and with some form of exploiters, as we'll see in a moment, this bias can be reduced by quite a bit. So that's pretty useful here. Okay, so they have created a multiple agents and even different types of agents in this league training scenario, out of which the main agents are the ones which use these techniques we just talk about to continuously improve at solving the game better or learning the game better. Okay, then there is another class of agents which is called which are called main exploiters, which basically exploits these current agents. So they test these agents for weaknesses. So again, as you can see here, these agents, if they are biased towards one direction, the exploiter's job is to basically, yeah, exploit it, so that since here this unit overpowers this unit, it forces the model to have high variance and not be extremely biased in one direction. Okay. The third class of agents is league exploiters. These exploit the entire league, and what that means is they are basically trying to improve everything in the league. So like the entire gameplay itself, rather than just focusing on one particular type of agent. Okay. So this is what it looks like, and all of the experiments here, as I said, has been initialized by the supervised learning method. So as you can see, each of these three races up until this point, they have the weights or the parameters after the phase supervised learning phase. Okay, so okay, so these are the main agents, the main exploiters, and league exploiters, as we talked about, and these are the three races. Okay, so these main agents play against themselves, their past versions, as we have shown here, and they continuously improve to obtain the final version, which is the best agent for each of those races. Whereas the main exploiters, what they do is they improve in the job of exploitation, but after they have achieved a certain exploitation, they reset to the supervised learning. So it's basically to prevent bias in the exploiters themselves. So since they reinitialize from the supervised learning weights, they are able to complete, like they are able to exploit new strategies in agents, if that makes sense. Okay, so as we can see, they basically target the main agents, whereas the league exploiters, they have a similar, yeah, they have a similar strategy as main agents, but they also reinitialize, because again, they periodically reinitialize, because at every stage you want to sort of find new aspects of improvement, right? So these two reinitialize, whereas this is a continuous training to obtain the best agent possible. Okay. Let's talk about the architecture now. So this is the complete agent architecture, and there are certain inputs and outputs to this, which we'll discuss now. So okay, so this is the backbone or the common base, whereas this acts as the critic. As you can see, it predicts the value, and this section acts as the actor. So it predicts the action in a as a series of steps. So as you can see, it first decides what kind of action to take, what is the expected delay if this action is supposed to be queued and repeated. And let's say if the action is something like selecting a certain set of units, then which units are need to be selected, where do we need to put them, and the exact position of on the map of where this is supposed to take place, right? So yeah, so basically the determination of action is a pretty sequential and structured process, and that is how they have been able to break down this huge combinatorial action space into something which is more manageable. Okay, let's talk about the critic over here for a minute. So as we remember, the critic also uses opponent information. That is what is included in the baseline features here. whereas scalar features and entities, as you can see over here, are the other sorts of input, which are basically unit type, some position of those, the attributes, and all those kind of details. These are mainly scalars or vectors. Whereas the minimap here are grid kind of data, and they have several layers, as you can see over here. So the minimap here basically encodes all the spatial information, whereas these encode all the scalar, vector, and entity based information. Okay, the LSTM here is pretty important because that is the only memory component which takes into account all the previous states, as you can see with this loop, and that is supposed to sort of remember the actions this agent has made, and so on and so forth. Okay, uh, after this point it forks into the actor and the critic, as we talked about. So i guess the I guess the two or three main points over here, or the components to look at, are the transformer or the attention module, which have been pretty significant recently in providing performance gains using attention based techniques. The second is pointer network, which given a list of inputs or a list of units can effectively select which inputs do we need to be taking action on. And finally they have this skip connections, which they have introduced at these later stages of selecting units and targeting units. This have provided a huge benefit, as well, as we'll see later on. So this is what their entire architecture looks like, and the more details can be found in their supplementary work. Okay, so now we'll discuss the results. So the first aspect of it is model performance. So this is the graph, as you can see. So we have AlphaStar supervised, which is just the supervised learning phase and stopping the training after that. AlphaStar mid is reinforcement learning after some 27 days of training, whereas AlphaStar final is the fully trained version, nearly 44 days of training. Okay. MMR over here is matchmaker rating. This is provided by StarCraft, and there are human players. Uh, the best human players are somewhere in the Grandmaster League at 6,000, something like that. So AlphaStar was able to reach pretty close and actually beat most of the human agents. Okay, and this is what their performance MMR numbers look like. So for each one of those races, you can take a look at that. So these are the number of matches won against matches conducted, and so on and so forth. So these are the average ratings for each one of those races. Okay, so the main takeaway from this slide is that all of these techniques, all of the reinforcement learning in combination with supervised or imitation learning, all of that works, and it is able to make this AlphaStar model reach at the Grandmaster level. Okay, let's talk about the benefits provided by the league training now. So with this graph, you can see that there are a number of agents. So in the league training, there are a lot of agents being trained simultaneously, right? But they basically fall within the three categories we discussed. So main agents, league exploiters, and main exploiters. So I guess the main thing to take away from this is that as the training progresses, the main agents are constantly being improved upon until they reach their final stage, whereas the main exploiters see a bit of decrease, which points to the fact that these agents, although they are improving their ratings, they are also less exploitable as the training goes by. So elo rating, by the way, is a relative metric, which means you gain points relative to how strong or weak your opponent is. You might have seen this if you play online chess. Okay, so this is again showing the test elo and the benefits provided by adding each one of those type of agents. So just having the main agents reaches to an elo of 1540, and as you can see, adding each of those components gives us some benefit. Okay, next the self play techniques are discussed over here. So as you can see, again, just fictitious self play, prioritized fictitious self play, and just even the normal self play has high elo, but thing to be noted here is that these are more forgetful. So If you remember, self play only plays with the current version, so it runs around in circles and it is more exploitable basically. And finally, a combination of all of this, the prioritized version as well as the basic vanilla self play, gives the best elo. Okay, yeah. With this figure, what we are supposed to note here is the exploitability or the versions of previous versions of agents that are used in the current version. So as you can see, somewhere around as the basically the training goes by, you can see these horizontal lines or the extent of this horizontal lines reducing, which basically means that these agents uh, do not need much training or are not much exploitable by some previous agents, which means as the training is progressing, this entire AlphaStar system is not just running around in circles, but it is indeed becoming less exploitable. Okay, so I guess those are the main takeaway, that the league training improves the ratings and reduces the exploitability, and the self-play techniques make this thing less forgettable, less forgetful, and therefore more robust. Okay, so that's pretty impressive. Now let's see an ablation study of the architectural choices. The Okay, so this is a pretty important graph. As you can see, if we do not have any human supervision or human game replays or something to have as a supervisory signal, the ELO rating is quite low. Which goes to show basically that this is a very difficult problem for reinforcement learning from scratch. Okay, as we just train the supervised component, and if we stop there, this is the elo we get. Human init here means just initialized from supervised, and then pure reinforcement learning takes ahead from that. uh, and these two are, as we talked about, addition of pseudo rewards, and these are able to improve the elo significantly, right? So with all of these techniques, we have supervised, we have sparse reward reinforcement learning, and then pseudo rewards, which finally gives us the best elo. Okay, so as for the modules or components in the architecture, adding the delays also gives some improvement from the baseline, because as we'll see in a moment, the delays actually help in avoiding micromanagement too much and focusing on long-term strategies. So delay provides a certain benefit, but pointer networks, which are responsible for selecting units, transformer, which are responsible for entity encoding, and the scatter connections, as you saw those connections in the later stages, are pretty important in improving this performance. So these architectural, like the at least these three modules give the most performance gain. Okay, uh, yeah, this is again an important graph, meaning where this is the one where critic without opponent information is shown to perform quite horribly compared to when the critic has opponent information. So this is, I guess, a pretty important takeaway. Okay, so now comparing the update rules for the actor and critic. So adding vtrace provides certain benefits. Adding td lambda learning for the critic also provides some benefit, and finally the upgo technique, which was introduced in this paper, also provides some technique, some improvements. Okay, yeah. So the takeaway here is that initial supervision is crucial. Just pure reinforcement learning does not take us very far over here. And pseudo rewards also simplify this RL training procedure. Finally, the architectural tools we have used over here are are pretty important in determining the performance. Okay, so now let's talk about how fair this AlphaStar agent is. So as you can see over here, the actions per minute of in blue you have AlphaStar, versus in red you have the average human player. So for each one of those races, the lines which shows the mean here is pretty close or less than what the number of actions humans can make in a minute. And this is the effective actions per minute. So this is when grouped actions are separated, and this is basically uh, the ultimate actions which are made by the StarCraft II engine. So this is, I guess, a more reliable metric, but in either case, you can see that the alpha star does not exploit the system by taking too many actions compared to what a human can. Okay. Okay, so in this graph, as you can see, when we increase the APM limit, we expect that the ELO rating or any performance would, the performance of the agent would go up, right? But what is surprising is that after a certain point, there is no improvement, but there is rather a reduction in performance compared to when we see the ELO rating, right? So this shows a curve rather than just a linear increase. And the takeaway here, first of all, from these graphs is that the effective actions taken by AlphaStar is comparable to humans. So it is not exploiting in terms of numbers of action. And even if it were given unlimited number of actions per minute, as we can see over here, taking too many actions in a minute forces the alpha star, or provides alpha star the incentive to focus too much on micromanagement, right? So then it forgets basically high level strategies which are crucial for actually winning the game, and focuses more on micromanaging if alpha star is allowed to take too many actions in a minute. So that is the takeaway here. Okay, so now that we have covered almost all important topics, it's time for the final remarks before ending this presentation. The first point is heavy reliance on imitation. So even though we have developed these sophisticated RL-based techniques and training regimes, we still need the initial supervisory signal. So is this a hint towards a computational limit if we were to do this in a purely RL-based manner, or is there something else? The other point is that the critic uses opponent information, and this is not very much aligned with how humans learn. Humans always have partial visibility even throughout the process of learning this game. So this is something which seems a bit off. Okay, there are some after analyzing a lot of games, so like experts like Arctosis have done, there are, even though AlphaStar has gotten very good at beating humans, it still exhibits certain strange behavior or some silly uh, cases where which could have been easily avoided. So I just show them a couple of them here. So this is something called Cannon Rush, where AlphaStar is the Zerg race while the human player is Protoss. So this simple maneuver, which should have been avoidable by AlphaStar, by someone of AlphaStar's caliber, it still does not could not avoid it, even though it eventually won the game. So another use case is where AlphaStar follows a pretty popular strategy of building a wall. It is the Protoss race here, but it did so incorrectly, having units deployed in one gap. But since it did not place this structure correctly, there was another opening over here through which the Zerglings were able to enter. So it suffers with exactly placing the structures where they need to be. Okay, so all of these are details. Okay, so the final point I want to make here is this is amazing work by DeepMind, in that the model is not too heavy. It's just some 50 million parameters during inference, which is lightweight compared to some recent models you might have seen. So it is, and the training strategy seems fairly robust. So this is some amazing work, but what other applications can we think of this? Because it would certainly be very beneficial to the RL community, right? So that's the note I want to end up on. That's it. Thank you for your time.